Hi everybody, I'm Letz, working at Lyon on the Faust language and ecosystem, and today I'm going to present a work we did last year on the idea of hybridizing Faust and Soul, and Soul is a new domain-specific language for audio DSP. To our best knowledge, Faust was the first compiled language for audio DSP, being able to do sample-level computation. But since recently we have seen several interesting projects like Soul, a new language developed by Julian Storer, the father of the JAWS framework, and Cesare Ferrari in 2018. And more recently we saw this internal new language done by Elastic Audio, which aims to be used into the domain of games, and basically which is a domain-specific language, data flow stream-based approach with a flavor of functional programming. And both of this language and also Faust is using the LLVM compiler technology, which is an interesting and efficient technology to define and develop new domain-specific languages. Obviously today I'm going to focus more on Soul and explain this idea of hybridizing Faust functional programming approach and Soul imperative programming approach, doing some demo and give you some perspective. Since we are at the International Faust Conference, I'm not going to present Faust as a language, and we are going to go directly to the compilation model and the compiler. So the Faust compiler has to synthesize the most efficient implementation for a given target language. So we have this kind of scheme going from block diagrams and internal representation into the compiler, computing, generating signals. Then we have an intermediate version called FIR, which is Faust imperative representation. It's basically a state-based representation. And from this FIR, we are able to generate C, C++, LLVM IR, or Soul, or more recently, WebAssembly, or even bytecode for an interpreter. C++ was the first target, allowing to do some kind of static compilation, but with LLVM IR, we are able to embed the compiler itself with the libfaust library and do dynamic compilation from DSP to executable code in a plugin or in an application, for instance. And we can do the same kind of dynamic compilation using WebAssembly on the web. The code generation model, basically the compiler flattening the block processor, does symbolic propagation and computes the output signal equation. And then we can either generate a giant big DSP loop, generating sample one by one, or we can have a DAG of separated loops connected with buffer, and this second model is more adapted when we want to do auto-vectorization. So assuming the final compiler like C++ or LLVM can do auto-vectorization. We have so this multi-target model, and then we have the architecture file second step. Basically the compiler outputs either a C++ class or a LLVM module or a WebAssembly module, and this code, which describes the DSP itself, has to be connected to the external world, like the audio layer, which can be a core audio or jack or ALSA driver, but also to the control interface. The control interface can be a standard graphical user interface with a slider or buttons, but could be also OSC or MIDI or sensors, and you can even combine several control layers to control a given DSP. So we have this multi-target model plus the architecture file model that allow us to have this multi-target ecosystem at the end. So from a given DSP source, we can generate plugins and standalone application and web application, and since recently we also target embedded devices like Bella, Daisy, Tinsy platforms. When we want to generate Soul, we obviously have to look at Soul source code. It's an imperative and procedural language, but it's sold by their developer as a domain-specific language, but also as a runtime, so a platform that is going to be deployed on specialized hardware. So it's an imperative and procedural language, but with some hard-coded additional concept like this processor and graph model that is used to describe DSP. So the processor is going to describe the processor unit, DSP unit. You have to implement a run method that will be called to compute each sample one by one. And this run method has to call an advanced method to give back control to the graph execution engine. So it's a coroutine-like model. And then processor have to be connected with a special syntax to create graph, and you can have graph inside the graph. Then you have to describe how control parameters are going to be used, and you have basically two models, either using an event-based plus callback model or a stream-based approach. We can look at some example of source code, a simple example and a more complex one. Here I have the simple example, so it's only a processor that is going to play a lick of pitch. Each pitch is played, so you have here the run method, and you have the play note, which play a given pitch using an oscillator, and you have this advanced method at the end to compute the next sample. A bit more complex example with this reverb. So basically this is a Soul implementation of reverb. It's at the higher level you have the graph, you have the description of control parameters, then you have the connection part, which is going to connect processors that will be described later on into the source code. Then you have description of all pass filter, so you see this run and advanced model. The same for the comp filter. You have some additional processor to do mixing and implement parameter ramp, and at the end you have like 300 lines of code to describe the Freeverb in Soul. Compiling to Soul, so we have added a new Soul backend into the Faust compilation chain. Basically, we directly generate Soul source code using the scalar model, one big DSP loop, and we generate automatically the description of slider button coming from the Faust source code, and they are compiled as input event and callback handlers. We have developed additional architecture files like this fall DSP Soul code that basically allows to deploy polyphonic objects, the same with an effect, and we can do a demo using the Faust IDE. So I'm switching to the Faust IDE. I have here a physical model of clarinet that I can run in Faust IDE. And then I can export it to Soul, platform and Soul monophonic architecture. I compile it again, download the resulting files. I'm switching my screen now. Here you see the result. So basically it's a folder containing two files. First, the Soul code itself. So you see the clarinet model, processor, and a piece of code, and then you have the run method here, which giant inline code, and the advanced method here. And we also have an additional JSON description, like a kind of entry point of the Soul code. So we can just copy, paste this code into the Soul program here. So I'm just pasting my Faust to Soul converted code. I compile it, and here I have my clarinet running into in Soul, and I can change parameter here, freq, bend, play it again. Okay. So I was just basically using the Soul playground, so it's a web implementation of the Soul compilation chain. We have developed additional tools like this Faust to Soul script to compile Faust to Soul and run the result with a Soul runtime. I can demonstrate that. So we have some additional option to, if you want to describe polyphonic instrument. Here I can play with Faust to Soul, play a given Faust DSP code here, and it's running into the Soul runtime. Now we have experimented this idea of hybridizing Faust and Soul at a deeper level, but looking if we could mix in the same source code a piece of Soul and piece of Faust. So basically we have added a new extension into the Soul syntax, so it's an experimentation for now with this Faust processor syntax, where you can put Faust code into a Soul source code. And basically we are going to extract those parts and compile them to Soul and put them again into the original Soul source file and have a giant Soul text file that you are going to compile to the Soul runtime. We have developed a Soul Faust player tool to demonstrate the idea. It compiles Faust section to Soul, and then at the end we deploy with a Faust runtime, Soul runtime and a Faust GUI. I can also demonstrate that. So here I have an hybrid code. So here you see a Faust processor, so with pure Faust code, and now you have Soul piece of code, so the classic ringtone we saw just before, an echo written in Faust, and then the graph part that basically connects everything together, and we can compile this with this Soul Faust player, and we have this result. We have still some limitation because of limitation in the Soul language itself, so it's still experimental in some sense. The perspective now at the language level, we may try to do a more deeper connection with the Soul compilation chain by using HART, which is an internal language representation into the Soul compiler, and possibly do some code introspection to better generate the code. The perspective for Soul developers, obviously they may use Faust DSP libraries compiling to Soul code and insert in some additional source code they have already written. And it's a way also to experiment this idea of mixing functional and imperative programming into a same source code. For a Faust developer, assuming Soul as a platform succeed, and assuming that they can deploy Soul on iOS, for instance, or on the web browser, or on specialized hardware, it will be for Faust developer a way to target new hardware, basically. We have done some benchmark by comparing Faust and Soul. Basically, we take a set of Faust DSP source code, We compile them to LLVM and run it into our Faust runtime, and versus Faust to Soul running into the Soul runtime. And you see the result here. Basically, the green part is Faust running in Faust runtime, and the red part in Faust going for Soul and running into the Soul runtime. And as you see, in general, the Faust code running in Faust runtime is still faster. We have done a more precise benchmark on the Freeverb, taking the Faust version of the Freeverb running in Faust runtime versus Faust Freeverb compiled to Soul running into Soul runtime versus a manually version of Freeverb code written in Soul and running into the Soul runtime. And we have this kind of result. So as you see, on the left you have Faust running in Faust runtime, and on the right you have Soul manually written code running in Soul runtime. And you have a factor of 2 basically. And if you run it with smaller buffer, the difference is even higher. And Soul in this case run much slower compared to Faust. And you can have those links if you are interested to go deeper. You have the Faust sheet, the development we did with Faust and Soul tools, and Faust IDE, and 2 links to look at Soul. Thanks for your attention. Thanks a lot.